Welcome everyone to our lesson on exponential and logarithmic functions. In this unit, we'll uncover how exponential growth and logarithmic relationships describe many real-world phenomena, from finance to biology. Understanding these concepts will strengthen your algebraic reasoning and prepare you for future calculus topics. Let's begin exploring how these two types of functions connect and why they are so powerful in modeling change. By completing this module, you'll be able to identify exponential and logarithmic relationships, analyze their graphs, and apply them to real situations. You'll also solve equations and compare how changes in parameters affect the shape of each curve. These outcomes are not only mathematical but also analytical. They train you to think quantitatively about growth and change in any context. Our main reference is College Algebra by Stewart, Redlin, and Watson, Chapter 4. Sections 4.1 through 4.7 cover everything from exponential definitions to logarithmic scales. Make sure you read carefully and attempt the examples provided. They bridge theory and practice. A good strategy is to summarize each section in your own words before trying the exercises. This week includes 4 key activities. First, a discussion forum on compound interest to connect theory with finance. Second, an investigative assignment where you'll model exponential and logarithmic data. Third, a written assessment to test your mastery. Finally, a web-assigned quiz to strengthen computational fluency. Together, these ensure both understanding and application. An exponential function has a variable in the exponent rather than the base. For instance, f of x equals 2 to the x grows extremely fast compared with a linear function. Even small changes in x can produce huge variations in y. This quality makes exponentials ideal for modeling population growth, radioactive decay, and interest accumulation. Let's explore their basic properties. In this section, we're introducing a new family of functions known as exponential functions. For example, the function f of x equals 2 raised to the power of x is an exponential function, where 2 is the base. What makes exponential functions special is the speed at which their values grow. When x equals 3, the function equals 8, and when x equals 10, the result is 1024. This rapid increase shows how exponential functions model processes that grow or change very quickly, something we'll continue exploring in the next slide. Let's review the formal definition of an exponential function. We know that the laws of exponents remain valid even when exponents are real numbers. An exponential function with base a is written f of x equals a to the x power, where a is greater than 0 and not equal to 1. If a were 1, the expression would always equal 1 and no longer represent growth or decay. This general definition forms the foundation for every exponential model we'll study, whether it involves population, finance, or natural phenomena. Here are some simple examples of exponential functions. When f of x equals 2 to the x power, we call 2 the base. It represents doubling behavior. For g of x equals 3 to the x power, the base 3 means the function triples each time x increases by 1, and h of x equals 10 to the x power uses base 10, which connects directly to our decimal system and scientific notation. Each base changes how quickly the function grows, but all share the same structure, a to the power of x, and pass through the point 0, 1. To understand shape, we plot selected x values and compute their corresponding y values. Connecting those points produces the familiar exponential curve. Notice the steep rise or fall and the constant crossing at 0, 1. Graphing by hand reinforces comprehension before relying on graphing calculators. When we change the base a, we generate an entire family of exponential curves. Smaller bases below 1 produce decay, larger bases create faster growth. Despite differences, all share the same intercept and asymptote. This family illustrates how a single formula type can describe many behaviors in science and economics. We distinguish two types: growth, when a greater than 1, and decay, when 0, less than a less than 1. Growth functions increase rapidly as x rises. Decay functions decrease rapidly as x increases. Both pass through 0, 1. Recognizing these two categories will help you decide which equation fits a real-world trend. When analyzing exponential functions, it's important to recognize that the x-axis acts as a horizontal asymptote. This means the curve approaches but never touches the x-axis. When the base a is greater than 1, the function a to the power of x moves closer to 0 as x becomes very negative. Conversely, when the base is between 0 and 1, a to the power of x decreases towards 0 as x grows larger. The graph below shows several exponential curves, some rising, others decaying, but all leveling near I equals 0. This consistent behavior defines the boundary that exponential functions never cross. Every exponential function f of x equals a to the x power has domain negative infinity to infinity and range 0 to infinity. The line y equals 0 is a horizontal asymptote the graph never crosses. These consistent characteristics simplify graph identification and problem solving. Understanding them is key before we examine inverse functions. What about comparing exponential and power functions? When graphing an exponential function beside a power function, you'll notice something remarkable. At first, the power function grows faster, but after a certain point, the exponential curve accelerates and surpasses it completely. This turning point illustrates the difference between multiplicative and additive growth mechanisms. It's why exponential patterns dominate in compounding, viral spread, and population dynamics. Exponential formulas also describe how money grows through compound interest. If you invest a principal amount P at an interest rate I per period, after one period, the amount becomes P times 1 plus I. After 2 periods, the new amount is P times 1 plus I squared, and so on. This repetitive multiplication mirrors exponential growth, showing how reinvested interest accelerates total earnings. So, this formula shown here gives the total amount after a certain number of years. A of TE equals P times 1 plus R over N, raised to the power of N times T. Let's break that down. P stands for the principal, or the original amount you invest. R is the annual interest rate, written as a decimal. N is the number of times the interest is compounded per year. For example, monthly would mean 12 times. And T is the number of years the money stays invested. What makes compound interest powerful is that you earn interest on your interest. Each compounding period adds to your total, and that larger amount keeps growing exponentially. So over time, even small investments can grow significantly, especially when interest is compounded frequently and the money is left untouched. That's why compound interest is often called the magic of exponential growth. The annual percentage yield, or APY, translates compound interest into an equivalent simple rate. It tells investors the true yearly return regardless of compounding frequency. For instance, 6% compounded daily yields 6.183% APY. This measure allows fair comparison across banks and investment options. Understanding APY is an essential financial literacy skill. Let's look at an example of how to calculate the annual percentage yield, or APY, for an investment that compounds daily. In this problem, the investment earns interest at a rate of 6% per year, compounded every day. That means the interest is added to the balance 365 times throughout the year, once for each day. To find how much the principal grows after 1 year, we use the compound interest formula. A equals P times 1 plus R over N raised to the power of N times T. Here, R is 0.06, N is 365, and T equals 1 year. Substituting those values gives us A equals P times 1 plus 0.06 over 365 to the power of 365. When we calculate that, it simplifies to approximately P times 1.06183. That means after 1 year, the investment grows by about 6.183%, slightly more than the stated 6% rate because of the effect of daily compounding. Now let's talk about logarithmic functions. The logarithmic function with base a is defined by log x equals y if and only if a equals x is crucial, where a greater than 0 and a not y we can rewrite. This definition means the logarithm gives the exponent needed to transformation allows us to isolate variables. For example, log base 2 of 8 equals 3 always because verify which form better suits the problem. Understanding this reversal, the properties of logarithms follow directly from exponent rules. They include the product rule, log base a of ab equals log base a of a plus log base a of b, the quotient rule, log base a of a divided by b equals log base a of a minus log base a of b, and the power rule, log base a of a to the power of k equals k log base a of a. These properties simplify long expressions and are indispensable in algebraic transformations and calculus derivations. Because logarithms are inverses of exponentials, their domain and range swap. The domain is open interval 0 to infinity, and the range is all real numbers. That means logarithms are defined only for positive arguments. Always check the sign of the input before attempting to evaluate or graph log functions. The graph of y equals log base a of x is obtained by reflecting the graph of y equals a to the power of x across y equals x. It passes through 1, 0 and approaches the y-axis but never crosses it. There's a vertical asymptote at x equals 0. For a greater than 1, the curve rises slowly. For 0 less than 1, the curve rises quickly. 1, it decreases. This reflection visually confirms their inverse relationship. When we vary the base a, we get a family of logarithmic curves, each similar in shape but differing in steepness. Larger bases flatten the curve, while smaller bases make it steeper. Despite differences, all intersect 1, 0, and share the same vertical asymptote. These families reveal how base choice affects rate of increase. The logarithm with base 10 is called the common logarithm and is denoted simply as log x. It is widely used in scientific notation because powers of 10 naturally fit our decimal system. If 10 to the power of 1 equals 10 and 10 to the power of 2 equals 100, then log 10 equals 1 and log 100 equals 1, 2. To find non-integer values like log 50, we use a calculator's log key. Among all logarithm bases, one stands out, the natural base e, approximately 2.718. Logarithms with this base are called natural logarithms and are written lnx. They play a central role in calculus, differential equations, and continuous growth models. Understanding the natural logarithm of x gives us a gateway to advanced mathematical analysis. The natural logarithm is defined as ln x equals log base ex, meaning it's the exponent to which e must be raised to obtain x. It serves as the inverse of the exponential function e to the power of x. This relationship makes it especially important for modeling continuous processes like population growth or radioactive decay. When we graph the natural logarithm of x, we see a smooth curve that increases slowly for large x and approaches negative infinity as x approaches 0 from the right. Its mirror, e to the x power, rises steeply to the right and approaches 0 as x decreases. These two graphs reflect each other across the line y equals x, confirming their inverse connection. The natural logarithm shares all the standard log properties. ln AB equals ln A plus ln B, ln AB equals ln A minus ln B, and ln A to the power of k equals k ln A. Additionally, ln 1 equals 0 and ln E equals 1. These identities make it easier to simplify and differentiate expressions in calculus and applied modeling. The logarithmic function ln x is defined only for x greater than 0. This restriction means any argument of a natural log must be positive. If an equation contains natural logarithm of x minus 3, for instance, x must exceed 3. Checking these constraints prevents calculation errors and ensures valid solutions. The logarithmic function ln x is defined only for x greater than 0. This restriction means any argument of a natural log must be positive. If an equation contains natural logarithm of x minus 3, for instance, x must exceed 3. Checking these constraints prevents calculation errors and ensures valid solutions. In this presentation, we explored how exponential and logarithmic functions describe patterns of rapid change across mathematics and real life. We began by defining exponential growth and decay, comparing them to linear and power models, and applying them to examples such as compound interest. We then examined logarithmic functions as the inverses of exponentials, learning their properties, graphs, and uses in measurement systems like decibels and pH. Finally, we introduced the natural base E and the natural logarithm, key tools for modeling continuous change. Together, these ideas reveal how mathematics captures both explosive growth and steady transformation in the world around us. Today, we explored one of the most powerful relationships in mathematics: exponential and logarithmic functions. These two families of functions are deeply connected, and they appear everywhere in nature, science, and technology. Let's start with exponential functions. An exponential function has the variable in the exponent, for example, f of x equals a times b to the x power. The base b determines whether the function represents growth or decay. When b is greater than 1, the graph rises quickly, showing exponential growth, like a population that doubles every few years or money that grows through compound interest. But if b is between 0 and 1, we see exponential decay, like radioactive material breaking down over time. Notice that exponential graphs always pass through the point 0, a and never touch the x-axis. They approach it but never quite reach 0. Now, let's talk about logarithmic functions. These are the inverse of exponential functions. If exponential functions multiply and grow rapidly, logarithms reverse that process. When we write y equals log base b of x, it means that b to the power of y equals x. In other words, the logarithm asks, to what power must I raise b to get x? The logarithmic graph increases slowly, starting near 0 and stretching out to the right. Logarithms are incredibly useful. We use them in measuring sound with decibels, in the pH scale for chemistry, and even in data compression and computer algorithms. When you understand how these two functions mirror each other, one growing fast, the other undoing that growth, you begin to see how they model real-world change. Keep in mind that exponential and logarithmic functions are two sides of the same mathematical coin. Together, they describe how quantities evolve and how we interpret patterns of growth and decay in our universe. Today, we explored one of the most powerful relationships in mathematics: exponential and logarithmic functions. These two families of functions are deeply connected, and they appear everywhere in nature, science, and technology. Let's start with exponential functions. An exponential function has the variable in the exponent, for example, f of x equals a times b to the x power. The base b determines whether the function represents growth or decay. When b is greater than 1, the graph rises quickly, showing exponential growth, like a population that doubles every few years or money that grows through compound interest. But if b is between 0 and 1, we see exponential decay, like radioactive material breaking down over time. Notice that exponential graphs always pass through the point 0, a and never touch the x-axis. They approach it but never quite reach 0. Now, let's talk about logarithmic functions. These are the inverse of exponential functions. If exponential functions multiply and grow rapidly, logarithms reverse that process. When we write y equals log base b of x, it means that b to the power of y equals x. In other words, the logarithm asks, to what power must I raise b to get x? The logarithmic graph increases slowly, starting near 0 and stretching out to the right. Logarithms are incredibly useful. We use them in measuring sound with decibels, in the pH scale for chemistry, and even in data compression and computer algorithms. When you understand how these two functions mirror each other, one growing fast, the other undoing that growth, you begin to see how they model real world change. Keep in mind that exponential and logarithmic functions are two sides of the same mathematical coin. Together, they describe how quantities evolve and how we interpret patterns of growth and decay in our universe. Let's take a moment to talk about how to be successful in math class. Many students believe that being good at math means you're either born with the ability or you're not, but that's not true. Math is a skill that anyone can learn and improve with effort. What really matters is your mindset. Believe that you can improve because progress comes through practice and persistence. Every time you make a mistake, think of it as an opportunity to grow. Mistakes show you where your understanding needs more work. And that's how learning really happens. Stay positive even when the material feels challenging. Perseverance is one of the most important ingredients for success. Strong study habits will also make a big difference. Don't wait until the night before a test to start studying. Review your notes every day, even for just 10 or 15 minutes. Practice problems consistently, not passively, by writing them out and checking each step. Instead of memorizing formulas, focus on why they work. When you understand the reasoning behind the math, you'll remember it longer and apply it more confidently. In class, be an active participant. Ask questions whenever you're unsure, because if you're confused, chances are someone else is too. Engage with examples and discussions, and join study groups where you can explain ideas to others. Teaching is one of the best ways to reinforce your own understanding. When solving problems, take your time, read each question carefully, underline what's being asked, and break it into smaller, logical steps. Check your work using estimation or inverse operations to make sure your answers make sense. And remember to use your resources. Visit your teacher's office hours or tutoring centers. Online platforms like Khan Academy, Desmos, or GeoGebra can give you extra practice and visual support. Manage your time well by setting a study schedule and sticking to it. Finally, take care of yourself. Get enough rest before exams. Your brain performs best when it's well rested. Eat healthy snacks, take short breaks while studying, and keep a growth mindset. Progress matters more than perfection. Success in math isn't about being the fastest, it's about staying consistent, curious, and confident that you can get better every single day. As we reach the end of this unit, take a moment to recognize how much you've grown. Every formula you've learned, every problem you've solved, and even every mistake you've made has helped shape your understanding and confidence. Mathematics is more than numbers. It's a language of logic, creativity, and perseverance. Remember, true learning doesn't happen overnight. It's built one question, one effort, and one small victory at a time. Whether the topic came easily or challenged you deeply, what matters most is that you didn't give up. Every challenge you faced became a step toward mastery. Keep this spirit alive as you move forward. Approach the next topic and every future problem with curiosity and courage. Believe in your ability to reason, to discover, and to grow, because learning math is really learning how to think. As the great scientist Albert Einstein once said, it's not that I'm so smart, it's just that I stay with problems longer. Let that be your reminder. Persistence is your greatest tool, and your effort is what makes success possible. Congratulations on completing this unit. Keep learning boldly, keep questioning deeply, and always remember every equation you solve brings you one step closer to understanding the world.